Welcome to this explainer. Okay, today we are going to completely unpack an everyday magic trick that happens, well, millions of times a day, right under our noses, or actually, right under our feet. I'm talking about the incredible physics behind how vehicles stop. It's one of those things we totally take for granted every time we go for a drive, but the science making it happen is absolutely fascinating.
I mean, really think about the sheer scale of what's happening for a second. You've got a human being, specifically one human foot, just casually tapping a pedal. And on the other side of that equation, you have a massive machine made of steel, glass, and rubber, weighing literally thousands of pounds, hurtling down the highway at 60 miles an hour. It is the ultimate David versus Goliath mismatch. A light tap from your foot shouldn't mathematically be able to command a 2-ton piece of moving metal to just stop on a dime. The stakes are incredibly high, the physics are immense, and yet it happens smoothly every single time. So, how exactly do we win this physical tug of war?
Well, the secret lies in a surprisingly simple principle. A small force applied over a small area creates a much larger force, giving you mechanical advantage. That right there is the whole trick. It isn't magic at all. It's just a brilliant application of hydraulic force. So in this explainer, we are going to completely unpack exactly how this incredible mechanical advantage works out there in the physical world. We're going to look at the hardware, the step-by-step action, and the underlying laws of physics that take that tiny little effort from your foot and amplify it into a force powerful enough to bring a speeding car to a dead halt.
All right, let's dive right into this. To really understand the physics, we first need to look at the mechanical setup. Hydraulic brakes use a special fluid, appropriately named brake fluid, to transmit the force from your foot on the pedal all the way down to the brake pads at each individual wheel. But, this fluid doesn't work alone. It travels through a highly engineered closed loop. Let's set the stage here and meet the cast of components that makes all this possible. Honestly, think of these 5 components kind of like characters in a highly coordinated heist movie. If one fails to do its job, the whole operation falls apart. First up, we have the brake pedal, which is where you apply that initial mechanical force. Second is the master cylinder. Its job is absolutely crucial. It converts your physical pedal force into hydraulic pressure. Third, we've got the brake lines and hoses, basically the transit system that carries this highly pressurized fluid to every corner of the car. Fourth, we reach the wheel cylinders, or calipers, which take that hydraulic pressure and convert it back into mechanical force. And finally, the muscle of the whole operation, the brake pads or shoes. These are what physically press against the rotor or drum to create the friction needed to actually slow the vehicle down.
Let's trace how this builds, step by step. When you press the pedal, you are physically pushing a piston into that master cylinder we just talked about. That piston then compresses the brake fluid inside the cylinder, which instantly generates hydraulic pressure. Now, because this brake fluid is essentially incompressible, that pressure doesn't just get absorbed. Instead, it travels instantly and equally through the brake lines, almost like a baton being passed in a perfectly timed relay race, heading straight out to all 4 wheels. Once it gets there, the magic happens. The fluid pushes against a piston in the caliper, effectively multiplying the force. And finally, that amplified force pushes the brake pad against the spinning rotor. Boom! The friction converts the kinetic energy of your moving car into heat, slowing the wheels and bringing you to a safe, controlled stop.
It's just an incredibly elegant sequence of events when you think about it. But this brings up a massive question. What exactly makes this pressure transmission so perfect? Like, why doesn't the energy just fizzle out or dissipate along the way? How can a fluid, something we normally think of as, splashy and yielding, act like a solid, rigid steel rod connecting your foot to the wheels? To get that real aha moment of how this entire system works, we have to look at a fundamental rule of physics.
And that rule is Pascal's law. Listen closely to this definition, because it's a real game changer. Pressure applied to an enclosed, incompressible fluid is transmitted undiminished to every part of the fluid and to the walls of the container. Now, the 2 most absolutely vital words here are enclosed and incompressible. Because the brake fluid is trapped inside those lines with literally nowhere else to go, and because the fluid itself cannot be squeezed into a smaller volume, the pressure you create up at the master cylinder doesn't weaken, not even a little bit. It is transmitted undiminished. It's exactly the same pressure down at the wheels as it is right under your foot.
So wait, how does equal pressure result in a larger force? Well, that is where the math comes in, and honestly, it's pretty beautiful. Pressure, which we'll call P, is equal to force divided by area. So the pressure at the pedal equals force 1 divided by area 1. But remember, because Pascal's law tells us the pressure is transmitted undiminished, that exact same pressure P also equals force 2 divided by area 2 down at the wheels. The pressure remains equal everywhere in the whole system. So because P is a constant, if you change the area in this equation, the force absolutely must change to keep everything perfectly balanced.
And this brilliantly illustrates how engineers use that math to our massive advantage. On the left side of our system, up at the master cylinder under your foot, we have a relatively small piston. That's force 1 applied over a small area 1. But on the right side of the system, down at the wheels, engineers intentionally design the wheel cylinder piston to have a much larger cross-sectional area, area 2. Because the fluid pressure hitting that larger area is exactly the same as the pressure created by the tiny area, the resulting mechanical push, force 2, has to be significantly larger to balance the equation out.
Now, what's absolutely fascinating is how this formula spells out your mechanical advantage in black and white. If we just rearrange that earlier equation to solve for our final output force, F2, we get this. F2 equals your initial foot force, F1, multiplied by area 2 divided by area 1. Basically, this means the difference in the sizes of those two pistons is literally your multiplier. If the area of the wheel cylinder is 10 times larger than the area of the master cylinder, your foot's stopping power is instantly multiplied by 10. The fluid pressure, it's really just the messenger. The difference in surface area is what actually does the heavy lifting here.
So the crucial point to take away here is that this mechanism isn't just unique to your car's brakes. It is the exact same principle used in a hydraulic jack. When you see a mechanic just effortlessly pumping a tiny handle to lift a 4,000-pound car up into the air, they are using Pascal's law. A small force applied over a small area creates a massive force over a large area, granting them an incredible mechanical advantage. Whether you are lifting heavy machinery in a garage or clamping down on a brake rotor while flying down the highway, the fluid dynamics are doing the exact same amazing job.
To bring this all together into a quick summary for you, the anatomy of the brake system converts your physical effort into hydraulic pressure. Pascal's law then steps in and guarantees that this pressure is transmitted equally and undiminished in all directions throughout that incompressible fluid. And finally, the intentional difference in the piston areas, a small master cylinder passing pressure over to a large wheel cylinder, explains exactly how that initial force gets so dramatically amplified. That right there is the pure physics of how a light foot tap conquers thousands of pounds of moving metal.
Which leaves us with a rather fascinating thought experiment to wrap up on. Looking at the math, where your output force is entirely dictated by the ratio of those two areas, if you made the wheel cylinders large enough and kept your master cylinder small, could your foot theoretically stop a moving train? I mean, according to the rigid mathematics of Pascal's law in hydraulic force, as long as you have enough incompressible fluid and a large enough area to push against, the mechanical advantage is essentially limitless. So the next time you tap your brakes, just remember the immense, amplifying power of the physics working right beneath your feet. Thanks so much for joining me for this explainer, and keep questioning the science behind the everyday world around you.